Hello everyone. In this video, we are going to talk about control of the robotic manipulators using computer vision. So we can call it vision-based control, or another name that we talk about would come in this area would show itself in many literature books and papers and so on. Is called image-based visual servoing, or IBVS. So what is it? So that's basically you have a camera, and this camera or several cameras are either attached to the fixed environment, observing the task space of the robot and what robot does, and try to guide the robot to what it should do. Let's say the goal is to do a pick and place, or grab something on the assembly line, or pick something on the assembly line, or anything like that. And if you want to, let's say, correct the end effector orientation or the location of it or anything, one of the things you can do is to basically take advantage of the cameras. Now, one time the camera could be on, as I said, on a fixed, let's say, wall or another object in the environment, so it is fixed with respect to the work frame. The other case is the camera is attached to the robot, okay? It's attached to the end effector, so we call it camera in hand, okay? And it is attached to camera. We're going to talk about both of those. Or, you know what, let me talk about them right now, about these two different ways that you can use computer vision data. So if the camera is fixed to the environment, okay, then what are the advantages and what are the disadvantages? Let's talk about that right now. So the advantages, the camera is fixed to the work frame, and regardless of how the robot moves, the field of view of the camera, right, the area that the camera can see, the relative sizes of the objects on the environment compared to the with respect to the camera frame, they are not going to change, okay? So that makes many of the mathematical calculations much simpler, right? Many of the rotation matrices and other things are not going to be used because the camera is fixed with respect to the word frame. What's the bad thing about it? The bad thing is when the robot comes on the way of the camera and occludes the field of the view, then the data from the camera cannot be used, right? So let's say here, for example, if I go back to one of my previous examples, let's say this robot that I have here. So let's say I want to observe how this robot is writing, right? Or grabbing something from the assembly line. So let's say, for example, here, this is an assembly line. This is a part of a conveyor, this flat piece. And now let's say I have some objects for this end effector to pick. Let's say this something like this, like some bottle of water or so. Okay, now one way is here. This is the wall, and here I have the camera, okay, fixed to the wall and observing the robot. As long as the robot does not come on the way of the camera, this one can probably give you a lot of useful information. We're going to talk about it. But if this object is, let's say, here, for example, and when this robot comes to grab it, this robot like this, it comes into the way of the camera, and this arm here, this guy, this big one, it is going to what? It is gonna, actually this part of it should not really move. That's a fix one, right? And then because of that occlusion, you're not going to get much of a useful information from that. So that's the problem. On the other hand, the camera, instead of being attached to the environment, could be attached to what? It could be attached to the robot at the end effector, or many times you're not going to exactly put it on the gripper or something, because gripper should be used to grab something. You're going to put it attached to the end effector, but not exactly in the middle of the gripper. You put it at some offset distance and maybe a little bit of rotation with respect to the end effector to get the best visibility in all conditions. This one that is attached to the end effector, or we call it the robot in the hand, in the palm, that gives you a lot better visibility compared to a fixed camera. The bad thing is, as you get closer to the object or further away, the field of view can change drastically. Okay, and the rotation matrices and everything that you had for the end effector, the position of it that you had from forward kinematics, they will be included in your relation for computer vision. Okay, because again, the position of this with respect to that camera is not going to be fixed. It's going to get closer, it's going to get further away, and the field of view, right, if this is your camera, the field of view, which is basically a cone, right? So this is, if you see the camera from the top, you have this angle here, right, which is called the horizontal field of view. So this is the top view of the camera. And if you also see the camera from the front view, right, then you will see again something similar. And this one, again, you have some angle. This one is called vertical field of view. So this is like front view. So in general, you will have basically a, let's see if I can draw something for you. This is the center. So you will have this kind of truncated cone. Of course, it's not exactly like that, so it's where all of these lines would kind of intersect. It's going to be here, really. Okay, so you have this cone. It has two angles, horizontal and vertical field of view. And of course, when you are closer to the object or further away, the amount of the area around the object and from the object that you would see would drastically change. Okay, so going back, we'll learn about two different ways to set up the camera in the environment, the advantages and disadvantages of each one. In this video, the method we are going to talk about is the second case, that the camera is called eye in the hand, eye in the palm. We assume that it is attached to the end effector because we want to be able to see the object that the robot is going to interact with all the time, even if it makes the mathematics parts of it a little bit harder. Okay, so that's one of the things that we do. It's eye on the hand. The other thing that we do, and I mentioned that here, it is a camera with a fixed, when you say fixed camera, it means fixed focal length. Okay, so when it's a fixed camera, means the focal length of the camera is not adjustable. Okay, we assume it's a very simple camera. You cannot change the focal length of it. And we use the simplest model of a camera, which is called the pinhole model, that it is here, and I'm gonna go over it very fast. And here the focal length, which we show with parameter lambda, is a fixed number. So these are the two things that we are going to assume in this video. And we're going to talk about how we use the data from these cameras to control the robot. There are two approaches called position-based visual servoing and image-based visual servoing. and we're going to use the second approach, but let me first give you some background about computer vision, and then we talk about these two different methods, and that we use the second one. So first thing first is, how do you model a camera, right? How do you talk about projection of the world onto the camera image plane? So here again, we are using the simplest camera model, is called the pinhole model, which is used for perspective projection. Now, let me tell you that very soon I will start a playlist called Image Processing and Computer Vision. Okay, and in that folder, in that playlist, I'm going to create lots of videos and train you on image processing and computer vision. So this video is just going to be a brief summary of a few videos in that playlist. So what is it that we are doing? Here we assume that the camera is like a what? The camera is kind of like a box, right? And the whole world is coming through what? A small hole in that camera. And it is going to be projected onto this back plane here, which is called image projection plane, right? Which you can see here, this plane that is shown with pi, right? Image plane. And if you have an object here in front of the camera here, like this arrow, for example, how is it going to be projected on the camera? So the rays coming from different points on the camera are going to reach this plane, right? And then here you have two triangles. That these two triangles, if you just look at it in 2D and from one side, you have basically two triangles that are similar to each other. So here is going to be the picture of the object, this one. Let me try it a little bit better. And again, as I told you, we use the similarity of these two triangles, this one and let's say this one here, these two. Since these two triangles are similar, we use the similarities, and that similarities would give us relation between the coordinates of point P, X, Y, and Z, which are in camera frame. Okay, so this P is not in the word frame, it is in the camera frame, P equal X, Y, and Z. If we, again, so this P is here, the coordinate of point P, but projected onto the camera frame, not in the word frame. So this is P in C, we show it with X, Y, and Z. We can relate those X, Y, and Z to what? To the projection of that point on the camera plane, on the projection plane, which here we show with two coordinates U and V, U for horizontal, V for vertical, that you can see here, the direction of these axes. U is basically from left to the right, V is downward positive, so from up to down positive. So you know, whenever you use a camera and take a picture, you project the 3D world into what? Into a 2D plane, correct? And basically use one of the dimensions, right? So now a few things. One is here you see that this projection plane that I have is what? It is behind this center of projection, the pinhole location, while here the center of projection here, this is the same as this point, it is now behind the image plane instead of being in front of it. Look at the relative position of the plane and the point. In here and here, you see they are different. Why? Well, the reason is what they do in this pinhole model and perspective projection is they do not consider the projection plane behind the pinhole. They bring it in front of it. Why? To avoid this reversal of the direction. As you can see here, the direction of the 3D world object and the direction of the projection are what? Upside down, right? The object is projected upside down. Unless you do what? Unless instead of that, correct? So we had, remember, we had this one. And we have this world object. Instead of using this here as the projection plane, and this distance, remember, if you call this distance from here to here lambda, which is, by the way, called the focal length of the camera. Now, if you bring that projection plane lambda in front of the pinhole, so bring it here, lambda units in front instead of behind, then what's going to happen? Now here, if you basically bring those rays to the pinhole, then they're going to intersect on this image plane here and here, and the object that you will get, the projection that you will get, is going to be what? It's going to be the same direction. So if that is standing upright, this is a standing upright, not upside down. So that's one of the things they do. They bring the projection plane lambda units in front of the center of projection or the pinhole location. Okay, to make this object again what? The same direction as the real world. Good. So this is called the pinhole model. This is called the perspective projection. What is perspective projection exactly? As I said, it's the relation between the coordinates x, y, and z and the coordinates what? U and v. How do I do that? I use what? I use geometry here. I use the similarities of triangles. Here it's going to be this small triangle, and then as well it's going to be what? This big triangle here, this one. So if I look at these two triangles that are similar, what is that going to give me? So let me do a little bit of cleaning here so we can see better. So you have two triangles that are similar. By the way, the z-axis here, the z-axis of the camera frame, you might say, what is camera frame? You keep saying camera frame. That's this x, y, z frame here that is attached to the camera. So this is like y of c, this is like x of c, this is like z of c. This is different from the world frame. This frame is attached to the camera. It moves with the camera. The z-axis of the camera frame is the one that is coming right perpendicular to the image plane coming out of the camera. Okay, that's the z-axis of the camera frame, and that axis is what we call what? The optic axis of the lens. Okay, so the z-axis is called the optic axis of the camera. Again, if I go back to that cone that I just drew for you a few minutes ago, remember we had these different angles, right? The z-axis is exactly perpendicular and outward. The x and the y, as you can see, are what? So y is like this, and x in this case actually should be this way, the way it is drawn. And it is, because if I want a right-handed system, then this x of c should be this direction. Okay, so it cannot be like that. Okay, so here I have changed the direction of x to make sure it is a right-handed system. We can say it's a left-handed system, but since we have been using right-handed so far, let's stick to that. And I added a c to them, so you know that these coordinates are with respect to the camera frame. Good. So Now, how do I use geometry here? Remember again, I have two triangles. They are similar. One of them, this vertical dimension of it, if you look, let's say if you look in this direction, if you just look in this vertical direction, in this direction, let's say perpendicular to the YZ plane or in the direction of X, what you will see is you have this height to be like V, and then you have this height to be your Y, and then you have this distance from here to here to be lambda, and then this distance from here to here to be your Z, correct? So when the two triangles are similar, it means what? It means lambda over Z is equal to V over Y. And if you cross multiply, what's your V gonna be? V is gonna be what? It's gonna be basically lambda Y over Z. And so this is your vertical coordinate in the image plane V. Similarly, if you look now in this direction, if you look in that direction, again, you are going to get two similar triangles. This time, this distance from here to here is going to be X. This one is going to be U. And again, you are going to get what? You are going to get lambda and Z. So this is your lambda, this is your Z. So your X, right? U over X is going to be lambda over Z. And so your U is going to be lambda X over Z. So now you can find your image plane coordinates. U is lambda X over Z and V is lambda Y over Z. And that's exactly what you see over here. So the simple geometry that takes you from XYZ to U and V is what I just told you. It is called the perspective projection, and it came from the pinhole camera model. So you clearly see that you go from 3D, which is XYZ, to 2D, which is U and V, and you lose one of the basically dimensions. Good? It's what you're really losing is Z. There is no depth on an image plane. You use what? You lose Z. You see Z here shows itself in the denominator. It's kind of become a hidden parameter. Okay, so that's U and V, the image plane coordinates. But is that exactly what you see on an image that you download from internet, right? You see it has 400 pixels by 200 pixels and so on. What is it on that? Is that exactly the same as this U and V? No. Here, if you look at U and V, they have the units of length. Why? Because X and Z, let's say if they have units of length, let's say they are both meters, and also lambda is a focal length, so it has unit of meters, then definitely if these two cancel, U and V are also gonna have meters for unit, or millimeters or something like that, right? But in an image, what you have is pixels. You have the object head, it's let's say at pixel number 200 horizontal and 400 vertical or something like that. So how do you go from unit of length, UV, to the unit of pixels, where for an image, the coordinates of a feature shown in pixel, we show it with R and C, the row index and the column index, because you know an image is basically a matrix. So how do you do that? To do that, we need two pieces of information. One is Sx and Sy. What are these? These are the dimensions of basically what we call your CCD, the sensor that receives all of these light intensities and convert them into a number, right? For either red component, blue component, or green component. Again, I do not want to get into image formation right now. That's a topic of its own. It needs a couple of lectures at least to talk about it. But on the camera receptor planes on the sensors of the camera that receive intensities of red, green, and blue. The sensor of the camera, okay, which corresponds to the size of your image plane, it has specific dimensions. So the whole width of this corresponds to so many pixels, we call it SX, and the vertical dimension of it corresponds to, again, so many other pixels, we call it SY, depending on how many of these pixels, how many of these receiving sensors are embedded in each direction, along each direction of what you call your camera reception plane, or you might just call it CCD. Right? So let's say, for example, again, it is corresponding to what? 400 pixels horizontal and maybe 500 pixels vertical. That's the size of an image that it can give me, or let's say it's HD, correct? So then what do you have here, right? If it's the basic HD, then what is SX and what is SY? Then you know this guy is like 1920 and this is 1080, right? If you have a wide screen HD high definition, these are the type of number of pixels that you get in each direction. Or if it's a standard small one, then it's like 1280 by 720 and so on, okay? So you need those. And the other thing you need is what we call the principal point, the location of the principal point OX and OY in terms of pixels. What is the principal point? So let's talk about that one. So remember we had the center of projection, or the location of the pinhole, correct? Here, the center of the camera coordinate frame, which is at the intersection of XC, YC, and ZC. Now, this ZC, this optical axis of the camera, when it intersects your what? Your image projection plane, it intersects it at a specific location, which is not necessarily the center. Many cases you might assume the intersection of the Z-axis with this camera projection plane is exactly in the center, half X, SX, and half SY, not always necessarily. It might be a little bit skewed and not exactly passing through the center, right? So it might not look exactly like that, correct? It might be something like this, for example. It is coming from, let's say, here. Right, so this location is not exactly in the geometric center of that plane. So that location, which here I showed with this blue circle, we call it principal point, and this principal point we show it with OX and OY, and the unit for OX and OY is, since they are compared to SX and XY, the unit for them are pixels. Okay, so they are in terms of what? They are in terms of pixels, as well as this SX and SY. Now, SX and XY are not just pixels, they are relating to pixels, because if you look here, the unit of them is actually meters per pixels or millimeters per pixels. So the unit of these guys is like this, millimeters per pixels. So they show you how many pixels are included in each millimeter of the CCD. Because let's say the CCD, for example, is 10 mils, right? Wide, and maybe 10 mils height. 10 mils high, 10 mils wide. But in that 10 mils wide, 10 mils high, in the horizontal direction, you have 1920 pixels, and in the vertical direction, you have 1080 pixels, right? So your SX is actually what? It is 10 divided by 1920, and it is 10 divided by 1080. These are the actual numbers of SX and SY, millimeters per pixels. So when I want to convert my U and V, which were in word units, in meters or millimeters, let's say, when I wanted to convert these guys, or let's say X and Y are kept in meter, but focal length is in millimeters, unless like it's a big telescope, lambda is typically in millimeters, then what you need to do to convert your U and V, which were in pixels, to row and column index R and C is you first divide them by SX and SY to convert them into pixels, and then this division, this ratio, is the difference between the actual location of the feature and what? The center. Or it's the amount of offset from the center. Right? And now everything works fine because U and V are now in mils, and SX and SY are mils per pixel. So definitely the unit of this ratio on the left or on the right is pixels, and here this is pixel, so we are good. So if we rewrite that relation, you will get these two important things. The row index is going to be the location of the center plus U divided by SX. The column index is what? Which is the location horizontally, I'm sorry. It is, again, OC, the location of the principal point C, plus V over S, Y. This OC and OR are the same as what I said, OX and OY. So let's write them that way so it is not confusing. So it is going to be, instead of X, we're going to have C. Instead of Y, we're going to have R. So this is going to be your principal point, okay? There we go. So now I have two sets of very important equations. One is this one, going from 3D world to 2D, and then going from 2D in units of mils to 2D in units of pixels, right? Combination of these two equations, this one and this one, are what we call in a camera intrinsic parameters of the camera. Okay, so when we say what are the intrinsic parameters of the camera, again, my goal is by no means I don't want to teach full computer vision or anything for you here. But when we say intrinsic equations, intrinsic parameters, what are the intrinsic parameters of the camera? As you can see, one of them is lambda, which is very important. OR, OC, SX, and SY. So you have 5 parameters inside the camera that go from 3D world to 2D. There are some extrinsic parameters for the camera, and those are the relation between this P, which you know it in the world frame, to this P, which what? You know it in the camera frame. So how would you go from P in the world to P in the camera? For that, you need to know the rotation matrix of the camera with respect to the world and the origin of the camera with respect to the world. Once you know those, you can go from here to here using a rigid body transformation or homogeneous transformation. And once you have PC, you can go inside the camera and get what? R and C. So these set of parameters here, by the way, we call them what? We call them extrinsic parameters, which are, there are 6 of them, right? 3 in O and 3 minimal orientation representations. So there are 6 of them here, and there are 5 intrinsic. So in general, a camera has 11 parameters, okay, that you need to find. And if you find all of these 11 parameters, the process to find these is called camera calibration. And again, we are going to talk about that in details in our future playlist called Image Processing Computer Vision. So I just wanted to give you some very, very brief explanation about the image formation model and perspective model. Good. So now let's talk about how we can potentially use the information in an image to control a robot that holds the camera attached to its end effector. So there are two approaches. The first approach, as I mentioned earlier, is called position-based visual servoing. The second approach for control is called image-based visual servoing. What's the difference? In the first approach, you try to take pictures from the object at different positions and orientations and use this data that you get from these different orientations and positions to build a what? Build a 3D representation of the world. A partial. You don't need the whole world around the robot to be modeled. You only, when it says partial, what in the world is it that you want to make a 3D model of? Only the object that you are trying to handle. You don't need everything else around that object to be modeled, okay? Only the parts that the end effector is to interact with, you try to 3D model that. So basically, this is kind of like a what? Is like a 3D scanner, right? When you have a 3D scanner, you move your scanner all over the object, correct? So let's say this is that water bottle again. And you bring this camera at all sorts of different orientations, different positions, and capture all sorts of what? Images. And then from these images, you try to reconstruct the 3D shape of this object. And then use that 3D information, which is going to be all of these points. You find their P of those points with respect to the camera. You make lots of these, and then you try to use that information to tell your end effector how to what? How to rotate, how to move, so that when the gripper comes right on the top of this object, it is in the correct position, correct orientation, let's say to grab it or place it down or anything like that. So this is the computer vision toolbox of MATLAB, and here are the examples. And if you go down, one of the parts in the example is, you can see it says structure from motion from two views or multiple views. So let's say if you look at this one, so this is this object, right? This is this globe. And here are 5 pictures taken from this globe at different positions and orientations. They are all on one side of the globe. They are not on all sides of it, just a little bit different in terms of position and orientation. You can see probably by looking at the location of that red spot. You see they are not exactly the same. And what you can do is, if you import the intrinsic and extrinsic parameters of the camera, then what you can do, you can estimate where were those 5 different position orientations of the camera with respect to the object. Here are some feature points. Again, what is feature points? What are these points that are used here? They found it in different images. They mash them together, and then they can approximate a rough 3D model of the object. As you can see clearly the base of the globe and most of the rest of the globe. And if you, instead of 5 pictures, you have now, let's say 100 pictures or so from different positions, orientations, you can estimate the 3D shape of the object a lot better. And once you connect these points together and make what we call tessellation, create surfaces, triangles from these points, then with a very good degree of accuracy, you can what? You can estimate the 3D shape of the object. And once you have that 3D shape of the object, then you can basically adjust your end effector position orientation to grab that object, to put it down, to handle it properly, okay? So this is what we call position-based visual servoing. What's the problem here? The problem is estimating this position, orientation, and finding this 3D structure of those points from all of these images is a time-consuming, computationally demanding operation. And when that's the case, performing it in real time for a robot is not going to be an easy job. Okay, because many of the computations for a robot have to be done in real time. And this is not something very easy that you can do, this 3D reconstruction from multiple views. This is not really something you can easily do in real time. So just wanted to know that there is such a thing, and that such a thing has a problem of computation. The second approach is we are not trying to recapture the 3D information of the world. Instead, we say no, whatever we see in the image plane is enough. We just stick ourselves to the 2D data on the image and forget about 3D, and try to design a control law for the robot based on the 2D features I see in an image, not 3D data. Like what? Let's say, for example, this is a bottle, okay? And I want to grab this bottle, right? And in order to grab it, or in order to do whatever I need to do with it, I want to make sure that my end effector, or the camera attached to my end effector, which sees the bottle right now as this, it sees it as perfectly horizontal. So right now, this end effector that is right above it, correct? It is not perfectly aligned. It is not perfectly aligned. So let's say the end effector is like this. Okay? The end effector is like that. And the camera that is attached to this end effector also, let me add it somewhere, let's say like this. This one sees the bottle like this, rotated and not being perfectly horizontal like this. So what should I do? If I want to see this guy completely horizontal, right? Then that object is fixed on the conveyor. One of the things I can do is to change the orientation of the end effector, right? So say, hey, let's spin this end effector so that it is now, let's say, rotated like this. And if it does, then the end effector can go down, the gripper can go down and properly grab it. So I need to find out basically what is this angle, required angle of rotation, right? That if I rotate the bottle through that angle, it makes it horizontal in the view of the camera, and that means now my gripper can align well with the two sides of the bottle and can go down and grab it and lift it. Right? So you see, what I'm trying to do is to just look at the 2D image of the bottle. And what I need to estimate is this rotation angle theta. How do I do that? There are so many different ways. One of the ways is to calculate the principal direction of what we call a blob. What is a blob? A blob is like a portion of an image that has uniform properties. For example, if the image is binary, which means black and white only, then if all of the image is black, a portion of it that is white only, that is a blob. Or if it's all white, like this, a portion of it that is all black, like this, can be considered a blob. Okay, so it has contrast with respect to the background of the image. And that blob, you can determine the location of the centroid of it, the moments of inertia of it, and then what? The orientation of it. And these are some simple what? Some simple formulas in the computer vision that if I have a binary blob, again means 0 and 1, So assume that the blob is 1 and the background is black. I can find the I and jth moment of the blob as summation of the row index of any point on the blob to the power I, the column index of any point on the blob to the power j, times the intensity at that location. And if the image is black and white or binary, then this intensity is either 0 or 1. Okay? So you can do all of this in Computer Vision Toolbox of MATLAB. If you have it, there is a command that does all of these calculations for you. If you don't, then you can write your own code. All you need is to be able to read the image in using the command imread. So here I show you an example. So this is the same blob, right? I made it black and white, but made the bottle white and the background black. And here I want to know what angle is it that I need to go from the x-axis, which is like here, go to the basically main axis of this bottle. So if this angle is theta, what is this theta, right? So that's the orientation of this blob here. How do I find it? Well, based on the formula I told you, you need to find the moments. So that moment ij that I just showed you, it is like this. If I go to a specific pixel like here, that pixel has a what? Has a row index and a column index in the image. So that location is like R and C, right? That pixel is pixel, let's say, for example, 100 vertical, and let's say, for example, 150 horizontal or something like that, right? So that is this pixel again. Let me make it a little bit bigger like that. That's that location. So whatever R is, whatever C is, I raise them to the appropriate power, I and J, and multiply by the intensity of the blob at that location, which again, this is a binary blob. So anywhere it's white, it's 1. Anywhere it's black, it's 0. So I multiply them by 1 basically. So for that location, the calculation I'm doing is whatever R is to the power I, whatever C is to the power J. And then what? I now move that pixel from that location to this location, to this location, to this location, and I cover all of the pixels. And then what? Sum all of this together for R values and for R C values, basically. And that gives me moment ij. Now, for different i's and different j's, it has different meanings. So if you find moment 1, 0, and divide it by moment 0, 0. What is moment 0, 0? Moment 0, 0 means the powers are 0, so it's going to be really 1. 1 with adding all the pixels together. So what does it really mean? It means adding all the pixels of the blob together. So this M00 is really an indication of the area of the blob. Okay? Says if you basically add the area, divide the moment 1, 0 to the area, that should give you R bar. And that's exactly the definition that we had. If you remember from your statics probably, if you had a specific shape and you wanted to find the centroid of it, what did you do? You had a special element, a specific element, dA, which was in location X and Y, if you remember. And then for X bar, you said it is equal to integral of X dA over integral of dA, or the whole A, basically. Right? And this is exactly the same thing, because if you look, the denominator M00 is this A. And what is M10? If I want to expand M10 for you, it is the summation of what? R to the 1, but C to the 0. So C is going to be 1, and intensity, if it's 1, so that's all it is, right? And remember, you do it only for a small pixel. Your small pixel that you calculate this term for counts as your dA for you. And what is R in an image, right? So R, if you do it, if this is R, then this is going to be R bar. If this guy is C, which is M01, because M01 is what? It is going to be summation of C to the power 1, R to the power 0 dA, right? So you are doing either summation of R dA over A, which is R bar, or you are doing summation of C dA, which is M01 over dA, which is M00, and that is C bar. So very similar. It's very similar to the definition that we had for centroid of an area. That's the exact same thing, but it's a blob instead of an area. So these two ratios will give you the location of the centroid. Then we find the central moment, Cij, which each location of each pixel is subtracted from the centroid, then raised to the power I and j, multiplied by intensity. And then this is, again, basically one of the things we had in statics. If you remember, in statics, if I wanted to find the principal moments, right? If I wanted to find the principal, principal axis, or the angle of the principal axis, basically, right? What was the angle of the principal axis? If you remember, back then we had tangent of 2 theta p was what? Was basically I xy divided by I xx minus I yy, right? And that's the same thing. Now you might have the division by 2 as well, but that's the very exact same thing that you see here in this formula. You see, this is your like Ixx, xy, this is Ixx, this is Iyy. So that is the principal direction, or the direction of the principal axis. So everything here is very similar to what you had in statics, and all I need to do here in MATLAB, if I show you this simple line of code, so I read that image that I just showed you in, I convert it into binary, and I can use, so here I read it using the command image read, and then I use im to bw, it directly converts your image into binary, black and white. And then there is this command called region props. If you pass the image to the region props, it can give you lots of different properties of that blob. And what are they? So if you go to the command region props, the properties it can give you is area, the shape of the bounding box, the corners of the bounding box, the location of the centroid, the circularity, the measure of the circularity, which is 4 pi times area of the shape divided by perimeter squared. This ratio is 1, it's perfectly circular. Different from 1, it's not going to be circular. You have the convex area, convex hull, eccentricity, Euler number. There are so many different things, field area. Then once you go down, one of the parameters is called orientation. And once you get orientation here, you see when I run it on it, it says the angle is what? Negative 34 degrees. And guess what? The angle here is really, if you calculate this axis and measure the angle of it with respect to the horizontal angle axis, this angle is exactly negative 34 degrees. So this is the angle that you have to rotate your end effector, not exactly equal to this, we'll talk about it, but if you rotate your end effector and the camera attached to it so that any point in this image rotates 34 degrees clockwise, then I can say now my end effector will be what? Right in the orientation position it wants to be, and now it can grab the object, correct? So that is the base for the second method of, we call image-based visual servoing, IBVS. What is this method? It tries to find in which direction the points of an image should move so that the object, the image coming from that object, the object is in a good position with respect to the robot end effector, the tool or anything. Okay, so we try to then form an error function. Error function is what? It is the desired location of those feature points minus the current location of those feature points. So if I can focus on specific feature points, and if I can change their position to a desired position so that it causes whatever I want to happen with the image, let's say in this case that 34-degree rotation, that is the kind of signal, the kind of error that I use to control my robots, okay? And we'll talk about it in the next video. But let's say in here, let's say if I have specific points on this, let's say blob, so I'll go back here and let's see if I can do some cleanup on here. If I find some specific points on this blob, let's say for example 1 point here, 1 point here, 1 point, let's say there, 1 point here, maybe 1 point here, 1 point here. What are these points? We'll talk about them later. We call them the specific feature points, right? They could be corner points, they could be any other types of points. But if I can always detect these points in whatever orientation of the blob that I want, and I can match them together, I say, well, I want, for example, this point, right, to go to here. I want this point to, let's say, go to here. I want this point to go to here. I want this point to maybe stay in the same place. This point maybe come to here. This point maybe goes to there, and so on. If these motions of these points can happen, right? Something like that, and so on, maybe this one here. Then if you do that, it causes that 34-degree rotation to happen, okay? So if I can calculate how much each one of these points should go, where are their desired position gonna be? So if I connect these yellow points together, I still have the boundary of the blob, but this time horizontal like this. That kind of difference in desired and actual location of the feature points is the kind of error that will drive my control signal, okay? And this is what we are going to watch in the next video. It's called image-based visual servo control, or IBVS. So, putting everything together, in the next video, we are going to see image-based visual servoing with the camera attached to the end effector. We call it camera in the hand. And we are going to create a control law based on these errors that I mentioned. There are two approaches. There is a simple approach that comes with problems, and there is a partition approach, which is more sophisticated, and that makes the control of the camera a lot more efficient, okay? Now, let me show you one more thing in the computer vision toolbox, since I mentioned these feature points. Again, the feature points is a topic of its own, okay? So my goal here by no means is to teach you about the feature points or so, but what is it really? So here we go again to computer vision toolbox. We go look at the examples. And one of the examples that might be useful to you if you look at it is this example, which is finding image rotation using feature matching. So what is it? Here is the cameraman picture. This is one of the famous pictures in image processing. And here is a rotated version of it and a smaller version of it. So these feature points are specific points that are easy to describe. They are either corner points or they have specific properties around them, the gradient of the color, light intensity, and so many other things that makes describing and finding these points much easier than any other random point in the image. Okay, so here the features that are found is using an algorithm called SURF. Okay, surf is one of the methods for finding feature points. So if you look here, the two images, the original image, which is upright and big, and the rotated smaller version, scaled version image, are laid over each other. And here, as you can see, there are a bunch of red circles and green pluses. And these are the same feature points that the surf algorithm could find in the two images, and they match each other. If you look, this circle here is at the elbow. The small green cross is also at the elbow in the rotated version, right? This feature here next to the ear of the person, again, the surf could find the very same feature in the rotated scaled version of the image, right? This point here on, let's say here, the tripod, again, it could find it and say, hey, that's this point, and so on and so forth, right? These 2 points on the knees, again, you see, it could find them on the knees. So not every point will be useful for feature matching. Why? What's hard thing about this? The hard thing is, whatever point that your algorithm, the feature finding and matching algorithm that finds and matches, those points should be robust to what? To rotation, to scaling, to translation, and so on. So for us, it's easy. For us human being, I can say, hey, this is the elbow, and then if I rotate it, if I scale it, if I move it, if I add some noise to it or whatever, I can again say, hey, look, this is the same elbow. So if I match this picture with that picture, I can probably say, yeah, maybe I have rotated the image by 30 degrees or so. For computers, for robots, it's not that easy. They have, all they give them is these two images, and these images are literally a bunch of pixels, a bunch of intensities, a bunch of numbers, two matrices, that's all it is, two matrices of numbers. How can it find specific locations in these matrices that whether I rotate the matrix, I scale the matrix, I do whatever I want, mess up with the matrix, it can still say, hey, this point is very similar to this point. And then by using a bunch of those points, by matching a bunch of those points, it says, hey, I can see a rotation, and that rotation is what? So when it does all the calculations and everything, it says, hey, I think you have rotated the image for 30.23 degrees, which is amazing, because we rotated it really for what? For 30 degrees. But comparing this original image versus this distorted, different version of the image, it can still give me a very, very good what? Estimation of the rotated angle. And if I know it's 30 degrees, guess what? I can rotate my robot and undo it, basically. So that's these features. There are different algorithms in MATLAB for detecting features between two images, and one of the methods is called SIFT. There is another one called SIFT, okay, S-I-F-T, and there are so many other new versions for feature matching. So that's how you generate a plot like this. These black ones are coming from what? The current image that you see. The white ones are coming from the ideal version of the image, which is laid horizontally. So if you have the ideal version of the bottle and the current version of the bottle, you can find these points through an algorithm like SIRF or SIFT, right? So one of them is going to be the actual position S, and the other one is going to be ST, the desired position of that feature point. And then using that, in our next video, we'll see how we form an error in the feature location, and then how we design a control law on how to move the end effector of the robot. Okay, so just wanted you to be referred to the right location in MATLAB, serve features and so on, because again, this idea of feature matching is way beyond the scope of this current lecture I'm talking about. In my future playlist, Computer Vision Image Processing, I will talk about this topic in several videos. So hopefully this video was useful to you, and I will see you in my next lecture. Thanks.